In this lecture, we're going to learn simple linear regression. Simple linear regression is the simplest form of studying relationship between two variables. One variable, we call it a response variable, or call it a dependent variable. For example, when we want to predict the height of a child based on the age, then the age is called a explanatory variable. Sometimes we also call it the independent variable. Some people also like to call it predictors. And the height in this example would be the dependent variable. Quite often, it's also referred as the response variable. Generally, we use y to denote the response variable and use x to denote the input or the independent variable. Here, we only have one of the x variable. In practice, quite often, there are multiple x variables. The principle of how to do the modeling and the interpretation will be similar. So here, we'll focus on the simple linear regression, which has only one x variable. Generally, we would have a sequence of observations observed for both x and y, the pair, like x1, y1, and x2, y2. x1, y1 is observed from the same setting, and x2, y2, that pair is from the same setting. Here's an example. Consider the response variable y is the OSA is talking about this is referring to about eye strain and irritation. And this y is the ocular surface area. And the x is the horizontal width of the eye opening. For this data, we would like to see how the OSA changes with the opening with the x. The first thing to do in the simple linear regression is always to make a simple plot, scatter plot. This plot, in horizontal axis, we put the x variable there. In vertical axis, we put the y variable there. And each of the points represent the observed data with the x and y given in the corresponding coordinate. This line is called the regression line. It was obtained by considering the minimizing the least square error. We'll talk about that in a little bit. So when you look at this plot, you can see for exactly the same x value, there might be the y values different. For example, if you look at these two points here, they have identical x values, but they don't have the same y. Another thing that you see is that these points deviate from the line, straight line. So straight line might seems to be the most plausible one, but each of the observed values still deviate. There's some variation in there. So we have part of the variation in the y is because it's changing with x, the straight line pattern. And another part of the variation is how each point depart from the line. And that's the part this straight line could not really explain. So right now, what do we see out of this picture is simply that there's a strong tendency that the y tend to increase as x increases. And there's also evidence of the linear relationship, pretty strong linear relationship between the variables. Once we see such evidence, we would like to try to estimate the slope parameter and the intercept so that we can use the line to predict for future observations. As you already saw, the plot contains some of the variations that's not in the straight line. And therefore, we write this model as a probabilistic model, meaning that the observation in the y can be decomposed as the mean of the y, and then plus some error part. The mean of y is that linear pattern. So here we have the beta 0 plus the beta 1x that represents that linear pattern. And the E here is simply the random error. Sometimes it's includes the part that we cannot really explain inside of that straight line. So it may not be totally random error, but the term is termed as random error, just so that anything that we could not really use straight line to explain, we put it in there. To estimate the beta 0 and beta 1, we make an assumption about the error. So generally, this error is assumed to have mean 0 and the variance to be sigma squared, a constant that should not change for different x values. And this linear part, the beta 0 and beta 1x, is simply the mean of y given the x value being x1. We call it a regression line or true regression line. This true regression line, sometimes the notation for that is written as the expected value E of y given x, when the x is the observed, x is the given input variable, independent variable. This could, sometimes the notation is also written as the mu with the subscript y given x star. That simply means what is the mean of y when the x's value is x star. Similarly, the variance of the y given the x value being x star, we use this v of y given x star to represent it. You can also use the sigma squared with the subscript y given x star. Both of them represent the variance of the response variable when x star is the input variable. For example, if x star is equal to 20, then the mean of the y given 20 would be simply just the beta 0 plus beta 1 times 20. And the meaning of the standard deviation, sigma of y given x star, is that the typical variation of the y around the straight line model is about this amount, is around sigma. That's the typical or average deviation. So as you saw, there's a straight line fit there, but you can draw many different lines. Which line should we use? The best line that we put in there is referred to as least square fit. And the parameter beta 0 and beta 1 estimated based on the least square principle are obtained based on minimizing this error of predicting an observation with the beta 0 plus beta 1x. That's the beta 0 plus beta 1x, that's the model part. And that model part compared to the observed yi, that's the deviation. When we take the square of that, that's the squared deviation. And look at all of the observations, we sum up all the squared deviation. This is referred as the sum of square error. And we try to consider all the beta 0 and beta 1 values, what value of beta 0 and beta 1 minimize this sum of square error. Whatever that is minimized, that's the answer for the beta 0 and beta 1. How is this beta 0 and beta 1 obtained? As you can see, this y minus the beta 0, beta 1. Once we have xi, yi observed, then the only thing unknown here is the beta 0, beta 1. Think of x and y are all those numbers, okay? So what you have is beta 0, beta 1, and inside of the square. And when you try to consider the sum of squared term, it's really a quadratic function. And for quadratic function, you can always try to find the value of those unknowns such that the value of beta 0, beta 1 had that make this function to be minimized. Let me try to explain with the iPad. Sorry, the iPad is not working. I couldn't really get it to work. So stop that. So just now we're talking about how to estimate the parameter beta 0 and beta 1. We try to estimate them by consider the sum of squared, the difference of the observed yi with the model beta 0, beta 1 xi. And this squared division, we would like to minimize it. It goes from 1 to n. And we call this one as a projective function. I'm going to write it as an L. It's a function of beta 0 and beta 1. Okay, it's L. L refers to the loss function of beta 0 and beta 1. And to minimize that, we would try to, so here this L is L beta 0, beta 1 is a quadratic function. Quadratic function of beta 0, beta 1. Well, this xi and the yi's are given numbers. These numbers, we do not really need to estimate them. They come from the observed data. So only beta 0 and beta 1 are unknown. So to minimize that, we know it's a quadratic function. So for quadratic function, what we can do is, here's a quadratic function. There's one point that will minimize that. And how to find this point? You simply take a partial derivative with respect to the parameter and set it equal to 0. Similarly, take partial derivative with respect to the other parameter and set it equal to 0. So you have two equations here to solve for two unknown parameters. Once we do that, it will give us the beta 1 hat is simply the sxy over sxx, and the beta 0 hat is estimate is simply the y average minus the beta 1 estimate times the x average. And what is this xy and sxx? That simply is this each of the observed x minus its average and the observed y minus its average, and take the product. We sum up of that. This is simply consider the cross of between x's deviation and y's deviation. That's the sxy. And the sxx, as you can tell, it would be similar, but it's going to be xi minus x bar, and then take the square. That's square deviation inside of the x variable. That's how we obtain this beta 0, beta 1 hat. This writing here, I'm explaining, but you do not really have to be able to derive that. Just know that we try to minimize the sum of squared error to find the estimate of beta 0 and beta 1. The next part, we'll go back to our regular slide, and we will continue with what's on the slide. Okay, so we have the estimate of beta 0 and beta 1, and what we would like to do is to consider some inference about the beta 0, beta 1. So-called inference generally is talking about that the estimate is a random variable. It will change from time to time, because each time you collect the data, you're going to have the x and y different from the next time when you collect the data. Therefore, the resulting estimate beta 1 hat and beta 0 hat would also changes when we have different samples observed. So to consider the inference, we will first need to figure out the distribution of beta 1 hat. And for this beta 1 hat, to think about the distribution, it's good to realize what is the random here and what is not. we have the sum over this cross product of x division with the y's division. The x is treated as a fixed value, observed given value, and the y, on the other hand, it changes as the random variable. So y's are the random values. So denominator sum of x minus x bar square, that's also treated as fixed value, and it's not random. So once we recognize that, we can see the y minus y bar and everything before that can be thought of as just some coefficient. So this becomes a linear combination of the yi's. And for linear combination of yi, we know that each of the yi, if we assume it's from normal distribution, then this linear combination of the normal random variable also will follow normal distribution. To make it simpler, we would rewrite this numerator of the beta 1 hat as the sum of xi minus x bar times just the yi. Why can we do that? Because the sum of xi minus x bar times y bar is simply 0. If that part is 0, it's no need to stay in there, and that which would only make the distribution of the beta 1 hat hard to obtain. But after we get rid of that, you can see that beta 1 hat is this linear combination of the yi's. And now we know that beta 1 hat is also normally distributed. When it's normally distributed, we just need to know what is the mean and what is the variance of beta 1 hat. From earlier chapters, chapter 5 in particular, we know that the linear combinations of the y, the mean of that is equal to the linear combination of the mean. And the variance is going to be linear combination of the variance but squared of the coefficient. So if you put in the yi using the expected value, the mean of y, which is the beta, you will find that the expected value of beta 1 hat will be just equal to the beta 1. And when you try to consider the variance of beta 1 hat, will have this xi minus x bar divided by sxx is taking squared of that. So you have sum and then the square of the coefficient and then times variance of yi. The variance of yi is assumed to be a constant sigma squared. So you have simply just the sum of this coefficient square times sigma square. And when you try to consider sum of the coefficient square, you'll realize that this ratio is simply just 1 over sxx. Therefore, what we get is the variance is equal of the beta 1 hat is equal to the sigma squared over sxx. What does this really say? Before we move on, okay, that when we take the square root, we'll get the standard error of beta 1 hat. The variance and the standard deviation says that denominator sxx, if that value is large, then the variance of beta 1 hat will be small. On the other hand, if sxx is not big, then this variance is going to be big. And what is sxx in the denominator? It's talking about the variation in the x variables. And we know x variables are given, they were not random. So for example, when you try to consider to study the height, how the height changes with the age is the x variable. Therefore, if you want the estimate of the slope parameter to be the beta 1 to be precise, meaning smaller variance, then you would like to have the age variable to have a very big variation so that they have different age range being considered. For example, you can have the age 10, 11, and then 12, 20, and so on. So these different values of the x, more of different variety, different values of x would help to increase the variations in x. As a result, because of SXX in the denominator, it helped to make the estimate of beta 1 hat to have small variance. We already learned in the past, small variance of an estimator means that the estimate is more precise. So that's the variance part. And we see that the beta 1 hat has normal distribution, and we already get the mean and the variance. So if we use the beta 1 hat minus the mean beta 1 and divided by its standard deviation is the one that's in the item 2, okay? Divided by its standard deviation, then it would have t distribution in this case. Here, why is the t distribution? Beta 1 hat minus beta 1 divided by the true standard deviation sigma of beta 1 hat, that is a standard normal distribution. But the denominator is not the true sigma. Instead, it's the estimated version. When we put the estimated version, just like how we did with the one sample t-test or two sample t-test, the statistic in the denominator, when you square it, here the s squared, the mean is the estimate of the standard deviation. When you square it and then multiply the n minus 2, it gives the sum of square of the error, and that sum of square error has chi-square distribution. So chi-square distribution divided by the n minus 2 in the denominator takes square root, and the numerator is the normal, standard normal. The ratio would be t distribution with n minus 2 degrees of freedom. So that gives us the distribution of this beta 1 hat. Once we have the distribution of beta 1 hat, we will be able to use it to help us to get a confidence interval about the beta 1 or conduct a hypothesis test regarding beta 1. So that's summarize what we learned in this first part of the simple regression lecture. We modeled the simple regression problem using a probabilistic model. The model specifies the mean of y given x is beta 0 plus beta 1x, so the linear pattern. Beyond that, there's random error in the y. And when we try to estimate the beta 0 and the beta 1, we try to make the error, mean squared error, as small as possible. And to minimize that, we simply treat this whole thing as a quadratic function of beta 0, beta 1. And the minimum would be achieved at the value such that beta 1 hat will be the s of xy divided by s of xx. And the beta 0 hat estimate would simply be average of the y minus the beta 1 estimate times the average of x. And the beta 1 hat is also a linear combination of the y's. And all the linear combinations with normal variable would still be normal if those y's are independent. So in our case, we can establish a distribution of beta 1 hat, which is normal. And the mean of beta 1 hat is equal to beta 1. Variance of beta 1 hat is equal to sigma squared over the variations in the x, sum of squared variation in x. And if we use beta 1 hat minus beta 1 and divided by the standard error, estimated standard error of beta 1 hat, then we get a t distribution, a t statistic that has n minus 2 degrees of freedom. Where is this n minus 2 from? Because originally we have n pairs of data, but we used some of those like n data pairs, we can use it to estimate n. We have n free pairs, but we estimated the 2 parameters, the beta 0, beta 1. So 2 of the degrees of freedoms are used. Therefore, the total free ones are n-2. That's why it's a t-distribution with n-2 degree of freedom. Next part of this lesson, we'll try to consider to construct the confidence interval with this distribution for the beta 1 hat. And we'll also do hypothesis tests about the regression.